In this chapter, we'll be looking at functions of several variables and the calculus behind them. In section 7.1, we just start with the primer on how to deal with functions of several variables. Up to now, you've only dealt with a function of a single variable, usually the x or t for time or maybe q for units. Now what we're going to be looking at is a function that takes multiple inputs and produces a single output. The single output is what makes it a function, but the fact that you can rely on multiple items to create that output makes it a more realistic situation. So let's start with some notation. So if we deal with just two independent variables and then the function variable, we sort of up it to a z, and we say that z is equal to f of x comma y. So instead of f of x, we now take an x and a y and enter that into the function to create some result. So the x and the y are called the independent variables because those are the ones that you enter into the function in order to produce a value. And the z is the dependent variable. The z depends on what values of x and y are chosen. Now that's just two independent variables and the dependent variable. But you can have more independent variables. You can have as many as you want. Let's take a look at an example that you're familiar with, but maybe that you haven't thought of in this context. Example number 1. Write the formula for the volume of a right cylinder. So a right cylinder looks like this. And what aspects do I need to know about the cylinder in order to create its volume? Well, I need r, which is the radius, and I need h, which is the height. You may know that the volume of a right cylinder is pi r squared times h. But now if I want to put that into function notation, we're going to say v of rh is equal to pi r squared h. So the independent variables are r and h, and the dependent variable is the v. The volume v depends on the values of r and h. Further, r and h are independent, meaning that they can shift however they want, with restrictions in this case. You know, you can't have negatives or 0 for either of these items, but they can be anything that they want, and they don't even depend on each other. You can have whatever height with whatever radius you would like. Example 2 says, find the volume of a right cylinder whose radius is 6 and height is 5. So if I use my function, then what this is asking for is v of 6 comma 5. Now notice that the order that you enter the numbers corresponds to the order in which the variables were named in the original function definition. Because they were named v of rh, then the 6 has to come first because that is the radius r, and the height 5 has to come secondly. But then we plug this in, and we get pi times 6 squared times 5, which is 180 pi. Just like with any other function, these functions have domain and range. So in the case where we have the x and the y is the independent variables, the domain is the set of ordered pairs in the form of x comma y that work in the function. And this can be anything from We need to take values out because they don't make sense in the context of the problem. For example, in the volume formula, we couldn't have negative r or negative h or even zeros for those values. Or it could be because the function has certain aspects that make it impossible to evaluate. Like you can't take the square root of a negative and you can't divide by 0. The range is still the set of values, but this time we call them z, that you get from the function. So they're just the values that are the results of using this function. In the previous example, when we had the volume, obviously we can't get 0 for a volume, we can't get a negative, but we could get anything else. Example 3 says, find the domain and range of z equals 3x plus 4y minus 5. Well, there are no square roots, and there's no denominator, so there's really no restrictions. So let's write it out as the domain is the set of ordered pairs x comma y such that, that's the big vertical bar, x and y are real numbers. So that's really not much of a restriction at all. And then the range, what kind of values could I get from this? Well, one way to think about it is to play a what if game. What if I just used any x, but I went ahead and said y is equal to 0? Then my z would be 3x plus 0 minus 5. And then I can think about, well, what is the range of this function, 3x minus 5? Well, you'll recall that that's a line that passes through negative 5 with a slope of 3, and that its range is all real numbers. And so I can get all real numbers for z by using a single value of y and then just using anything for x. Now, in general, we're going to be able to do multiple combinations with this because y doesn't have to be z, but this shows me that I will get everything somehow. And so this is going to be the set of z such that z is a real number. Example 4, find the domain and range of f of x comma y is equal to 1 over x squared plus y squared. So we have a problem with the domain, and that is that we have a fraction. And for the fraction, you cannot let the denominator, which is x squared plus y squared, equal 0. Now, how is it possible that x squared plus y squared is equal to 0? Well, if x is any number other than 0, squaring it is going to be positive, and y squared is positive if it's not 0. And so a positive and a positive, that's going to be positive. There's no way to, once you start with a positive, to get it back down to 0 because you're dealing with squared terms. So the only combination for x and y that leads to a 0 is if the x and the y are both 0 themselves. That's the only way. So we'll say that the domain is the set of ordered pairs x comma y such that the ordered pair x comma y is not equal to 0, 0. That's the only ordered pair I have to exclude. And then anytime I use any other x or any other y than 0, then we're going to get something positive, and that will evaluate. Now notice also it doesn't say that x can't equal 0. it says that x and y can't be both 0 at the same time. For example, you could use the point 3 comma 0 or 0 comma 3 inside this function because that is not the ordered pair 0, 0. And one of those is going to produce a positive number, which is not going to be 0 in the denominator. So those type things would work. Now what about the range? What kind of values can I get from this? Well, let's think about this denominator, x squared plus y squared. We now know that we can't use 0, 0. So that means anything I get has to be positive, which means it's greater than 0. Now, if I take the reciprocal of this, which is what my function is, it's the reciprocal of x squared plus y squared, and I take the reciprocal of a positive number, that produces a positive number as well. So 1 over x squared plus y squared is always positive, and that gives me the range. So the range is the set of z's such that z is greater than 0. It's not possible for me to get 0 exactly, and I can't get a negative, so that leaves me only with the positives. Now let's look at a function that has 3 independent variables right here and the dependent variable. And this one says let w equal the function f of x comma y comma z, and that be equal to 5z minus 1/2 y squared plus x. Find the value of f of 1 comma 4 comma negative 3. So here it's important to note the order of the variables when they are declared in the function. F of x comma y comma z. That means the x is 1, the y is 4, and the z is negative 3. So f of 1 comma 4 comma negative 3 is equal to 5 times negative 3 minus 1/2 times 4 squared plus 1. And if you work that out, you get negative 22. But it's the order of the variables because of the way they were listed that's important in this problem. In this next example, we're going to look at how to form the revenue function when you have multiple demands, multiple items, and multiple demand functions. Example number 6. The demand for computer tablets at a company is based on 2 types of tablets. P is equal to 700 minus 2x minus y, and Q is equal to 1200 minus 3x minus 2y, where P is the price of a standard tablet and Q is the price of the advanced tablet. And X is the demand for the standard tablet and Y is the demand for the advanced tablet. Question A. Find the weekly revenue function R of X comma Y. So in the past we had R of X is equal to X times P, where X was the number of items, and you that's the number sign, pound sign, and then P is the price. Well, we have the same thing now, but we just have to add in another version of that. So R of X comma Y is going to be the number of standard tablets times the price per standard tablet plus the number of advanced tablets times the price per advanced tablet. Well, the number of the standard tablets was X, and the price per standard tablet was P. and the number of advanced tablets was Y, and the price for the advanced tablet was Q. So it's very much similar to our original one variable situation, but we just have two different items, and so we multiply their number times their price and add that all together. So in this case, we're going to get X times the price, P, so 700 minus 2X minus Y, plus the number of advanced tablets, Y, the demand, times the Q, the price for the demand tablet. Now, don't get confused by the fact that the functions for P and Q include both an X and a Y. All that is showing is that the price for each of the types of tablets does not only depend on the demand for that tablet itself, but also the demand for the other tablet as well. So the demand for both tablets is influencing the price of each of them. And then we would multiply this out and combine. So we're going to have 700x minus 2x squared minus xy plus 1200y minus 3xy minus 2y squared. And then the only thing that combines here is the xy terms. And so let me write that. I'm just going to write it right here. So this would be 700x minus 2x squared plus 1200y minus 2y squared minus 4xy, where those two terms combined. Problem B, find the revenue when the demand for standard tablets is 200 and the demand for advanced tablets is 150. So this would be R of, now how did I write this? Well, I wrote it with X comma Y, and the X was standard tablets and the Y was advanced tablets. So this is going to be R of 200 comma 150. And so this will be 700 times 200 minus 2 times 200 squared plus 1,200 times 150 minus 2 times 150 squared minus 4 times 200 times 150. And you work all that out and you get 75,000, 75 large. Look at that. Part C. Suppose the cost function is C of x comma y is equal to 380 plus 120x plus 250y. Find the profit function. Well, profit is still revenue minus cost, but now we're going to have P of x comma y is equal to R of x comma y minus C of x comma y, which would be 700x minus 2x squared plus 1200y minus 2y squared minus 4xy minus the cost function in parentheses 380 plus 120x plus 250y. And then you would distribute the negative and simplify. And when you do that, you get 580x minus 2x squared plus 950y minus 2y squared minus 4xy minus 380. And that's your profit function for the tablets. D, find the profit of for standard tablet demand of 200 and the advanced tablet demand of 150. So this would be P of 200 minus 150. And so you can plug that into the profit function. So it'd be 580 times 200 minus 2 times 200 squared plus 950 times 150 minus 2 times 150 squared minus 4 times 200 times 150 minus 380. And we get a profit of 13,120. Next up is the Cobb-Douglas production function. This is a function that looks like this in this format here. And it says, in this case, f of x comma y is equal to k times x to the m power times y to the n power. This k is some constant. That's a number. And then x and y are the following. X is the utilization of labor, and y is the utilization of capital. And the thing that makes this, the Cobb-Douglas function work the way it does, is that the two exponents that you use sum up to 1. So basically what they are doing is you think about m and n as being sort of a percentage of the way that you are utilizing your labor and your capital into your business plan, your production function. So labor is how much you pay for work, and capital is how much you can invest in factories and machinery and things like that. And then this produces units of labor or specific quantities, whatever it is, because they changed it with the constant to utilize that. But that's how the Cobb-Douglas function works out. Let's see this example. Example number 7. The productivity of a coal mining company is given by f of x comma y is equal to 40 times x to the 0.6 times y to the 0.4. How many units of coal are produced by 1,000 units of labor and 300 units of capital? So in this case, we know that x is labor and y is capital. Now, in some other books, they use different variables and different things for constants. So you might see a K and an L for labor and capital. So it would probably be L for labor and K for capital. But you just need to read the context of the problem to see which one represents which. And that would be an M and an N, and there'd be another constant, maybe a C, something like that. So in this case, we have f of 1,000 comma 300. We plug it into the Cobb-Douglas function. And we get 24,712.3 units. And whatever the units are, right? It might be, wheelbarrows of coal or loads of coal or truckloads, whatever it would be. Whatever the meaning is to whoever came up with this function, that's the meaning that you go with. At this time, we want to look at how to graph in 3 dimensions instead of 2 dimensions. So in this case, the coordinates look something like this. It comes down, it comes out, and it goes across like that. And this continues down below the axis like that. Now this is a little bit weird, but the x-axis is coming forward. The y-axis is going over here to the right, and the z-axis is going up. And so if you have a coordinate, we'll say p of x comma y comma z, that's in 3 space. Then you come up the z-axis, however far that is. You go over the y, however far that is. And then you rise in space the z, however much that should be. So this is x, this is y, and then this is z up here. The space is divided into octants instead of quadrants, because oct means 8, and there are 8 different regions with positives and negatives, and that's how you graph. There's not a big emphasis on that in this course, but it is nice to know. So we'll go ahead and do these two. Plot the points A, which is 2, 3, 5, and B, which is -1, -3, and 2 on the same 3D grid. All right, so let me draw us a little grid here. Like that. So we'll mark this as X, Y, and Z. And let's do A. So we're going to come up 2, then over 3. So sort of this point here. And then from this point, we go up 5. So it'll be 1, 2, 3, 4, 5. Now, it doesn't look like it's going to go all the way up like that because of the perspective. So you just sort of draw it the best way you can. And sometimes people put little lines or little dash lines to coordinate with everything else. I'm going to do that one. Let's do it with a little thin line here. Just like that. Perfect. And we'll call that A. And now I'll do B in green here. So B says go back 1 on the x-axis, then back 3 on the y-axis. And so we'll form that little point there. Okay, there. And then it says go up 2. So we're going up 1, 2 like that. And so there's the point. Like so. Something like that. Again, the perspectives are all, slightly off because of the, the orthographic way that you're looking at the space and all that sort of stuff. But we just sort of do the best we can. But that gives you some idea about how the coordinates should work. Now let's look at some of the graphs in 3D. Example number 9 is a paraboloid. A paraboloid is an equation in the form of z equals x squared plus y squared. What is the absolute minimum of this paraboloid and where does it occur? So to graph the paraboloid, well, first we're going to graph the grid here, like this. And a paraboloid has x squared and y squared, and that makes little parabolas sort of all over the place, right? And we're doing this in space. And the way that they really denote sort of a paraboloid is by these little circles that you can see here. Sort of gives it like a little mesh, right, like that. But it is sort of a paraboloid, a parabola that is spun in space. The context for this is, think about a satellite dish. How a satellite dish is sort of circular, but it sort of goes up and around. That's a paraboloid. Now, what is the minimum value for the paraboloid? Well, the minimum value occurs right here. The minimum value is, absolute minimum value, is 0. And where does it occur? It occurs at 0, 0, 0. Right? So the domain value would be 0, 0, and then the z value, right? So this is the x, y, and then the z value is 0. And this is the point where it occurs, 0, 0, 0. Now, one type of curve that is of particular interest in this class is a curve that has what they call a saddle point. It's called a saddle point because the curve that creates it looks like a saddle. And so what you'll see here is, let me draw this one in green, is that you have this point right here where you have this curve coming around like this. And it goes behind there and sort of dashed like that. If you think about that curve alone, then this point right here is a maximum. But if you think about the curve that is right here, it comes up like that. It's sort of a little paraboloid, and I might be off on on one of the lines here, but you get the idea. If you look at this, this continues going up on both sides, then this same point becomes a minimum. So if you have a situation, and we're going to do this later on in a couple of sections, where by looking at one point on the graph and looking at the curves that create it, and one curve makes it look like it's a maximum, but another curve makes it look like a minimum, then that point is called a saddle point. We'll do more with that later on. Finally, we look at level curves and cross sections. So basically, we want to sort of dissect what these curves look like in 3D space by looking at horizontal planes and seeing what shape is cut out if you were to sort of slice the graph at that plane. Example 10 says, describe the level curves of f of x comma y that is equal to x squared plus y squared. Well, we know that this is our old friend, the paraboloid. Paraboloid. And it looks like this. Now, we were drawing these circles earlier to help us sort of see what the shape looked like. But those are actually the level curves that this problem is talking about. And so to find the level curves, you basically pick values of x, or z rather. Pick values of z, and then you analyze the graph in the xy plane. It's the graph that would result from picking that value. So let's pick some values of z. So let's say that z is equal to 1, for example. Then that would be x squared plus y squared is equal to 1, because z is equal to the f of x comma y value. And the question is, what graph is x squared plus y squared? Well, it's a circle. And it's a circle of radius 1. So in case you may have forgotten this one or didn't see this one in your previous class, a circle centered at the origin with a radius r has an equation that is x squared plus y squared equals r squared. And really what the equation of a circle is nothing more than the Pythagorean theorem. It's the Pythagorean theorem used with a fixed distance or fixed hypotenuse called the radius, and then you're rotating it around the origin to every possible point. Well, when you do that, you create a circle. All right, let's pick another value of z. Let's pick 2. So we get x squared plus y squared equals 2. Well, that's another circle. Its radius is the square root of 2 because of the way that the formula of a circle is written, but it's still a circle. And in fact, every time you have a positive z, you get a circle right back here for whatever z value that you want. And that's the plane that's being sort of tossed through the curve and cutting up the paraboloid. When it does that, wherever the graph intersects that plane, that's the curve that is the level curve. And it's also, you can think about it as a cross section of the graph in that respect with the z. Now, how do we classify all of these? Well, for any z greater than 0, you get a circle of radius square root z centered at the origin. Okay, so that's one classification. What about if z is equal to 0? Do we get anything there? Well, that would be the equation x squared plus y squared equals 0. And we've already talked about this particular type of problem. We know that that results in an x equaling 0 and a y equaling 0. So we get 0, 0 as a point. So the graph of that is, in fact, just the single point. So for z equals 0, we get single point, 0, 0. And then one more classification for any z less than 0. That would be the graph where, for example, x squared plus y squared equals -3, for example. And this can be any negative number here. Well, that can't happen. You have two squares that are added together. That has to be 0 or bigger, so it can never be a negative. So there is no graph. Now, what does that mean for the 3D graph? Well, that just means that there's a minimum right here. There is no graph down here below the XY plane. There's nothing down here. So that's what that results in. And those are the level curves that sort of help us to analyze the graph and figure out what's going on. What we use those for in the business class is if we have some sort of fixed rate of production or something like that, and we want to see the curve along which I can vary the capital or the labor and still have an equal amount of production being put out. And because then that affects the cost, because maybe I could find a cheaper cost by moving along that curve. So that's the business application for this, and we'll get into that a little bit later on. All right, thanks for watching. Have a great day.